Okay.
Okay.
Good morning, everyone. Welcome back to this third day of our meeting, Bandoleros. Thanks, everyone, for showing up. It's my pleasure to introduce Alexander Tikhomirov from the Higher School of Economics in Moscow, Russia. And he'll talk about the construction of symplectic vector bundles on the projective space P3. Alexander, please.
Thank you. Thank you. First, I would like to thank organizers for this possibility to give a talk here. I feel myself as I'm here in Campinas again. So my talk will be about concerning my joint work with Daniil Vasilyev from Moscow on symplectic vector bundles on projective space P3. The paper was published last year. What about moduli space of symplectic bundles? It is far from being well understood. By now, the only type of such bundles having satisfactory description are so-called tame symplectic bundles, which we will use in our construction of symplectic bundles of arbitrary rank and charge. I would say that it was shown by Ugo Brudzom, Dmitry Markushevich, and myself in two papers from 2012 and 16 that the moduli space of tame symplectic instantons are irreducible, generically reduced algebraic spaces of dimension presented by the deformation theory. And in this work, we will construct an infinite series of smooth irreducible moduli components of symplectic vector bundles of an arbitrary even rank. Rank is always even to R at least one, obtained by iterative use of monad construction applied to these tame symplectic instantons. As a particular case, we will obtain an infinite series of irreducible moduli components of stable rank 2 vector bundles on P3. We show that the series obtained here contains as a subseries a large part of the infinite series of moduli components of these rank 2 bundles constructed by myself and Sergei Tikhomirov and Daniil Vasilyev in 19. We also prove the existence result that for any integers n and r, where r is at least 1, of course, and n is at least r plus 147, there exists a moduli component, not necessarily unique, of our series, such that the symplectic bundles from this component have this rank 2r and the second Chern class n. And of course, our base field is always algebraically closed of characteristic 0. References. This our paper published last year, and our results are heavily based on, as I said, on two papers by Ugo, Dmitry Markushevich, and myself about these symplectic instantons, namely tame symplectic instantons. And the paper, the construction is motivated by that used in our joint paper with Sergei Tikhomirov and Daniil Vasilyev in 19. Okay. What is the idea of the construction? Let me recall first the construction of an infinite series of irreducible components of stable rank 2 bundles with determinant 0 on P3, given in this paper with Sergei Tikhomirov and Daniil Vasilyev. We take two rank 2 instanton bundles, usual instantons, E1 and E2, of charges m and n, respectively, where n is either equal to m or differs from m by a unit. And take an integer a, positive integer a, and consider the anti-self dual, shortly ASD, monad, of this type, O minus y, or O minus a at the left, the direct sum of these two instantons in the middle, and O of a in the right hand. I shorten the notation by O of I denote OP3 of I always. The surjection onto the right surjection is E, and the left surjection is left injection is called the transpose of E. It is just the transpose of E with respect to the natural symplectic structure on E1 plus E2. You know, any rank 2 vector bundle with trivial determinant is symplectic automatically. So we have a symplectic structure on the direct sum of these two instantons. Such a monad exists for A big enough and E chosen appropriately, so that to be an epimorphism. Let me denote by B0n, capital N, at least one, the Giesecke-Muruyama moduli space of rank 2 stable vector bundles on P3, with C1 0 and charged at the second Chern class, this capital N. In the paper in this paper, we show, in that paper from 19, we show that the cohomology bundle of this monad, which is the kernel of E modulo the image of E transpose, is a smooth point of a certain irreducible component. Let me denote this component by X, M, N, A, in the space of bundles with charge 0 and with determinant 0 and charge M plus N plus A square. It has the dimension given by this formula. And we show there in that paper that the components X, M, and A for these possible values of M and A constitute an infinite series such that for any n large enough, at least for n greater or equal to 146, there exists a component of our series lying in B0n. So this was a new series, infinite series of moduli components after the known series produced by instanton components and by the series of ion components constructed by Lorentz ion. Okay. The starting point of our present work is a very simple observation that the sum of two usual instantons, E1 plus E2, is an example of a rank 4 tame symplectic instanton introduced in our joint papers with Ugo and Dmitry Markushevich. Let me recall the definitions. By a symplectic instanton, we mean a symplectic vector bundle, E comma theta, of rank 2R, at least 2 on P3, with the symplectic structure theta, satisfying the conditions vanishing of E twisted by -2, which is just called the instanton condition, and the second condition, the vanishing of sections of E. some people prefer to give the definition where H0 of E minus 1 vanishes, which which follows from our condition. So it is more rough condition. But for us, in the present work, it doesn't matter. It makes no difference. So this symplectic instanton satisfies these conditions and has charge n, which is second Chern class, at least half of rank, at least R. It is well known, at least here in Brazilian mathematical community, that the symplectic instanton can be described in terms of hyperwebs of quadrics. By a hyperweb of quadric or of quadratic forms, I mean a homomorphism from the vector space K to the nth power tensor V to the dual of it, where V is the dual of the space of global sections of OP31. And this A should be symmetric or self-dual with respect to Kn and anti-self-dual with respect to V. So totally this is an anti-self-dual homomorphism. And it is known that to any symplectic instanton, there corresponds a hyperweb, which has rank 2n plus 2r, just depending on linearly in this way on its charge and rank, satisfying a certain open condition. Now, among all symplectic instantons, we distinguish the so-called tame symplectic instantons, which is defined by the condition that if we take the corresponding hyperweb and restrict it onto a subspace in Kn of power integral part of n plus r over 2 times V, we impose the condition that it is invertible. So this is, as you see, an open, the risky open condition. And in those papers, we have proved that the moduli space, which I will denote by now by INR, of tame symplectic instantons, is an irreducible, generically reduced algebraic space of the expected dimension, expected by deformation theory. So here is the formula for n times r plus 1 minus r times 2r plus 1. So unfortunately, it is a priori not clear whether it is a scheme, but because it is obtained as a quotient of the space of monads, which is of symplectic monads, which is locally closed subscheme of the space of all hyperwebs of quadrics by linear group. But inside it, we will distinguish a certain dense open subscheme, which I will define later. Okay. In our present work, we will construct an infinite series of mini-versal families of symplectic vector bundles, E comma theta, of arbitrary even rank and growing second Chern class, or shortly charge. We start with the general tame symplectic instanton, E0, theta 0, in I and R. By these rectangular brackets, I will denote the isomorphism class of a given symplectic bundle. two symplectic bundles E comma theta and E prime comma theta prime are isomorphic if there is an isomorphism between them compatible with their symplectic structures. That is, this equality is satisfied. Now look at the monad of the form like this, where in the middle you have this symplectic, tame symplectic instanton. I should mention that once we achieve that the right-hand morphism E1 is an epimorphism, which is achieved when A1 is sufficiently large, the twist by A1 is sufficiently large, then automatically E transpose, E1 transpose is a subbundle morphism, and the condition of this sequence to be a complex is automatically satisfied, because at the right and the left hand you have linear line bundles. So everywhere by the transpose of the right-hand morphism, we mean the dual of it composed with the symplectic structure. So we have an anti-self-dual monad, and the cohomology of it is always a locally free sheaf, that is a vector bundle. Let me denote it by respectively by E1. And on it we have a natural symplectic structure, theta 1, coming from the anti-self-duality of the monad. Okay. So the idea is just to iterate this construction. So we start with tame symplectic instanton E0, choose A1 and E1 so that to achieve the surjectivity, then automatically the left hand putting the transpose of it, we obtain the locally free homology sheaf E1. We proceed now with E1 with the very same way. Choose A2 large enough, and the morphism E2 respectively surjective, and so on. So we obtain the sequence of symplectic vector bundles from E0 to E1, etc. At the k step we have EK minus 1. At the k plus 1 step we have EK, etc. So this is the very natural idea to construct these new symplectic bundles. As soon as we start with the vector bundle tame symplectic instanton of high enough rank, you see that the set of thus obtained vector bundles, they have decreasing ranks. So at the last step, we will obtain the symplectic bundle of rank 2. That is familiar bundles for us, and they will be stable in the usual sense. So to summarize, for an appropriate choice of a sequence of these integers A1, A2, etc., ascending sequence, we recursively get a sequence of symplectic bundles of decreasing ranks, as I said, together with their symplectic structures coming from the anti-self-duality of the monads. Starting with rank of E1 is 2R minus 2, and the last one of rank 2, rank of ER is 2. So on each step, we obtain symplectic vector bundle as a cohomology of the monad obtained on the previous step. Let us remark that the monad construction of tame symplectic instantons, they also have usual monad description with the trivial bundle in the middle and the O of 1 to the nth power, respectively, its dual at the right and the left hand. And so each symplectic bundle which we obtain in this series actually is the homology of the Horax type monad, containing only, you see, this direct sums at the left hand, trivial bundle on the middle, and the dual direct sum on the right hand. So this is our other description of our bundles through monads. Okay, so starting with symplectic, tame symplectic instanton, we will obtain, we first distinguish a certain open subscheme. Let me denote it by Y T of this irreducible algebraic space I and R. And then adding the parameters for the choice of epimorphisms EK in the above monads, we thus obtain a sequence of well-defined smooth integral schemes, beginning from YA0, which is YT, to YAR minus 1, where this bold AK are the sequences of these numbers starting with 1 and then A1, etc., AK. And we will see that the bundles EK theta K constructed above will constitute mini-versal families of symplectic bundles on P3 with these bases Y bold AK. So we call these schemes YAK the moduli components of symplectic bundles. So our definition of moduli components is quite naive. It is just mini-versal families. We'll see that also that these sequences bold AK belong to a certain infinite countable set, bold A, which will be described below. And thus we obtain an infinite series, let me call it sigma, of all the possible YAs obtained this way. An infinite series of smooth irreducible moduli components of symplectic bundles with growing, arbitrary rank and charge on P3, and we'll give formulas for their dimensions. So please ask me any questions during the talk.
So Alexander, I got confused with this definition of the YAKs.
YAKs are obtained successively. I will show the procedure, how are they obtained. Okay. We start with YT, and then this is inductive proof obtaining YAKs.
Okay, thank you.
Mm-hmm. To start with, I would like to make a few remarks about Kodaira-Spencer maps for symplectic bundles. So let bold E comma theta be a family of rank 2R symplectic bundles on P3 with certain base X. And we may consider it as a symplectic vector bundle on bold X, which is P3 times X. Take any point small x in X and restrict this bundle bold E onto P3 times this point X. So we may look at the corresponding principal bundle of symplectic frames for E comma theta. Symplectic frame means just local basis in which the symplectic structure is given by a standard Darboux form. Then E, is recovered from this principal bundle as the associated vector bundle by a canonical representation of the symplectic group SPR in the space of K2R. I will use the following known fact about the deformation factor of principal bundles with symplectic structure group, respectively. As we see, this is the same as a deformation bundle for vector bundle E itself. It has tangent abstraction theory in which the spaces Ti of P are just equal to Hi of ed P, where ed P is the adjoint vector bundle, that is vector bundle associated to P via the adjoint representation of the symplectic group in its Lie algebra. And the adjoint bundle of P, this is a standard linear algebra, which I believe you will know very well, is just S square of E. So your symmetric square of E will be the adjoint bundle for P. Hence, Ti's are just Hi's of the homology of symmetric square of E. So, in particular, the Kodaira-Spencer map, shortly KS map, in the category of symplectic bundles is just the map from the tangent space of X at the point X to the H1, T1, which is H1 of symmetric square, is responsible for the tangent space to deformations of symplectic bundles. Well, in particular, when the abstraction space H2 of this symmetric square and H0 vanish, then we know that X is smooth at X and has the prescribed dimension given by minus Euler characteristic of S square of E, which is H1 of S square of E. Of course, H3 should be kept in mind that the last homology H3 of symmetric square of E is also 0, since H0 of symmetric square is 0, at least on P3. And then you know that once there is no abstraction, the Kodaira-Spencer map will be an isomorphism. And after possible shrinking X, the family E, our family E bold theta, is miniversal. Okay. So, our initial step, using this remarks from deformation theory, we will distinguish a certain smooth, we can distinguish a certain smooth, irreducible, dense, open subset, which is actually a subscheme in the modular space of tame symplectic instantons. Here we use the standard theorems of Rosenlicht about the action of reductive groups and generic smoothness, such that for any point in this open subscheme, we have there are satisfied these conditions that H0 of E0 vanishes, H0 of, by the way, all these are open conditions. For example, vanishing of H0 of a symplectic instanton is enough to check on direct sums of usual rank 2 instantons. So usual rank 2 instantons are just a very good example of tame symplectic instantons. Respectively, we check for a general tame symplectic instanton that they vanish also H0 of its square, of S square is 0. And the vanishing of the second cohomology for tame symplectic instanton is again, it is enough to check it for the sums of usual rank 2 instantons. But for them, you know that these spaces are smooth, so they have unobstructed deformations. I mean, H2 of endomorphisms, in particular of the S square of usual instantons, are 0. And so this implies the vanishing, generic vanishing of H2. Okay, then respectively H1 of S square 0 is of prescribed dimension, which is given by the formula mentioned above. And besides, there is, one can find a miniversal family of tame symplectic instantons with base YT such that for any bundle from the restriction for of it for onto P3 times any point in this open subset, the Kodaira-Spencer map is an isomorphism. Of course, you could ask me about whether this miniversal family is actually universal, at least locally universal family. This, I think one could afford this by shrinking YT, this base YT. But for us, it is not necessary. I mean, for us, it is enough to distinguish miniversal families. Okay, so this is the initial step of our construction, which actually follows from the more or less from our work on with Ugo and Markuszewicz on symplectic instantons. Now proceed to the induction step. So the first claim is that given an integral scheme and a symplectic rank at least 4 vector bundle on P3 times this scheme Y, which I denote by bold Y, There exists a positive enough integer a, which I denote by a of depending on y and e, such that for any integer a, at least this number a, and for any point y in the base of the family, bold script e, the sheaf script e or script ey, which is by definition the restriction of this family onto P3 times a given point, satisfies these conditions. These conditions are nothing but follow from Serre's theorem. This vanishing of Hayek homology and respectively the condition for H0. So H0 will then coincide with the Euler characteristic of E of A. What about an epimorphism? The second condition is that we always can achieve an epimorphism from EY to O of A when A is big enough. This is true for rank 4 bundles. If actually this is nothing but the condition of EY to be globally generated when twisted by A. So EY twisted by A should be globally generated. And this is using the symplectic structure. This is the same as the surjectivity of this map. And assume and we can also impose the conditions that E has no sections and respectively the square of it has no global sections. Okay, so this equality is 1 star together with Riemann-Roch, base change, and the symplectic structure of E show that if you look at the, so that H0 of E of A first is independent of the point Y, and by the base change, the sheaf H, which is pushed down by the second projection of E twisted by A, is a locally free sheaf of rank given by this number n, and we may consider the projectivized bundle P of H dual. This is a projective bundle, and if you use the second condition, 2 star, and look at those points in this projective bundle for which E at the point lying downstairs of X is epimorphically mapped onto O of A, that is just the risky open non-empty subset. Once Y is an integral scheme, then of course P of H dual is integral and also smooth once Y is smooth. And so X is also smooth scheme. And the morphism is smooth because the fibers are just open subsets of projective spaces. So on this, on X times P3, which I denote by this bold X, there is an anti-self dual monad with Ex in the middle, where Ex is just the lift of E onto this X via the projection pi. And L is nothing but the Grothendieck sheaf of this OX over Y of 1. And let us look at the bolt E, which is the kernel of the surjection. Capital bolt E modular the image of its transpose. As we have discussed, this E is a symplectic bundle since the monad is anti-self dual. So we have a symplectic structure, which I denote by theta, bolt theta E. So this is a way which Marcus, the way how this X is obtained from Y. And this is the step. If Y is YAK with K with given K, then X will be YA sub K plus 1. So this is the step of our construction of schemes Y sub AKs. Okay. Next, if we restrict our monad onto P3 times a point, then for any point X in capital X and Y its point lying downstairs, we obtain a symplectic or anti-self dual monad, which I denote as a complex by K bullet, with homology symplectic bundle capital E. We now consider the double complex K bullet times itself and its total complex T bullet, its symmetric part. So the interchanging of permutation of factors of the double complex induces the involution on T bullet. And so we may distinguish the symmetric part, which I denote the T bullet plus. So T bullet is just the direct sum of its symmetric part and anti-symmetric part. And the symmetric part has the form which outcomes from the original monad. So this is E minus A at the left hand, the dual bundle E of A at the right hand, and symmetric square E plus trivial sheaf at the middle. And what is about the cohomology? It has the middle cohomology, which is just the symmetric square of the cohomology bundle of original monads, that is S square capital E. If we pass to the cohomology in this complex and use the conditions 1 star and 3 stars, we obtain the exact sequence, which I denote by bolt A, of this type, H0 of E of A modulo K, H1 of the symmetric square of capital E of the homology bundle, and the symmetric square of original script E bundle. The last map, the right-hand map, let me denote it by eta. And also the vanishing of sections, respectively sections of symmetric square for this new capital A. On the other hand, if you look at the morphism from X to Y, this is a smooth morphism of smooth schemes. So for any point in X and any point Y downstairs, this point, we have an exact sequence of tangent spaces. So which we denote by sequence B. And this is H0 of E of A modulo K into the tangent space to X at the point X, and the differential at this point to the tangent space of Y at the point Y. Here, by construction, the fiber of pi is over Y is just the projectivized space of sections of E of twisted by A. Hence, the H0 this H0 of E twisted by A modulo K is just the tangent space to the fiber or vertical space at the point X. Okay, so let us now compare these two sequences. One can quickly guess that there should be a relation between them. Very well. One can guess what is the relation, and our claim too says that in the above conditions, let the Kodaira-Spencer map for the original bundle script E, which we denote by psi E theta at point Y, let it be an isomorphism. Then the exact triples A and B just fit in the commutative diagram. So these are so to say, the same sequences, where at the right hand we have this Kodaira-Spencer map for script E, the family, the original family, bold script E. And at the middle, we have the Kodaira-Spencer map for the constructed vector bundle bold E. The point is that so this diagram is the main technical tool of the paper. You can quickly guess that the right-hand square here is commutative. And the hard part is to check the commutativity of the left-hand square. So, though it seems very natural to be the case, the proof is quite technical. It actually takes 1/3 of our paper. So this is the main technical point, the whole paper. So from this diagram, we see that once the left-hand Kodaira-Spencer map is an isomorphism, then the right-hand Kodaira-Spencer map is an isomorphism. And therefore, once this X is smooth, we know that after possible shrinking X, the family bold E with its symplectic structure is miniversal. So at each step, we pass from a miniversal family of bundles E, script E, which stands for E with a number k-1, to the capital E, which stands for EK in the induction step. Okay. So now let me formulate the final results. So this is more, here is a certain notation. We denote by bold m r minus 1 the subset of sequences in ZR plus of such sequences where AIs are increasing. And take another notation for m r minus 1 in brackets. So collecting these above results, we obtain the following theorem that for given positive integers n and r, such that n is at least r and r is at least 2. So we start with, as I said, with rank more than 2, where rank is 2r. Let yt be a dense open subscheme of our space of tame symplectic instantons I and R with a universal family on it, described in the initial step. Then there is an infinite subset, which I denote by bold A sub n r minus 1 of the set m r minus 1, such that for any bold A r minus 1, which is the collection of 1, A1, etc., A r minus 1 is in this A, bold A and r minus 1, there exists a collection of smooth integral schemes, which I denote by YA0 up to YA r minus 1, and smooth surjective morphisms. You know, so this is a tower, you see, this is a tower of smooth morphisms, of smooth schemes, where Y0 is just YT. And AKs are the subcollections of the collection bold AR minus 1. Together with the universal families of symplectic bundles on P3 times Y AKs, such that the following statements hold. If we choose A sub k plus 1 as a maximum of the number A dependent on YAK and bold EK, which was defined in the claim 1, and the number AK plus 1, and we set A0 equal 1, then for any k between r minus 1 and 0, a k is an irreducible modular component of symplectic vector bundles of ranks respectively 2r minus 2k, vanishing sections of this bundle together with vanishing of its sections of the symmetric square of it, and the charge of E given by this number, and such that their spaces of sections, when twisted by AK, respectively by Hayek homology, are this. So Hayek homology vanish, and the H0 coincides with Euler characteristic. And each such scheme has a dimension, which I highlighted by this blue light color. The dimension is this one. So using this notation F sub 3 indices N, R, and A, where F is a polynomial of NRA, just presented here. You may see this formula. So this is, of course, generically they are, so to say, bigger than the expected dimension for symplectic bundles with this N and R, which was given by for tame symplectic bundles. And at each point of small y in this y case, each point is an isomorphism class of vector bundle, symplectic vector bundle, which is the homology sheaf of Horrocks type monad, as I noted before. And the Kodaira-Spencer map for this is an isomorphism. So the next theorem says that if we introduce some more notation to collect all the possible ranks and charges into the into one set, this capital A is a countable set, infinite countable set, defined this way, such that the schemes A sub bold A, where A belongs to this bold capital A, constitute an infinite series. So this is a very, very big, so to say, infinite series of smooth irreducible modular components of symplectic vector bundles on P3. And if we look at the final step of this inductive procedure, where we obtain a rank 2 bundles, so if I take A to be the collection of these increasing numbers from 1 to R minus 1, then there exists a generically smooth irreducible component B and A of the Giesecke-Murayama moduli scheme B0 capital N of stable rank 2 bundles on P3 with Chern classes C1 equals 0 and C2 equal N, where N is given above. This component has the dimension presented by this formula using that polynomial f. So it is again bigger than, so to say, than the prescribed dimension prescribed by the deformation theory, but nevertheless, we thus obtain an infinite series of which I denote, say, by pi, of this subseries of sigma of symplectic bundles of arbitrary ranks, where PR is just this subsequence of modular components of stable rank 2 vector bundles on P3. And as we said, our this series pi, capital Pi, contains a big part of that series, probably the whole of it, of that series constructed in our paper with Sergei and Daniil in 19. So the last result, which I will not comment, it is just purely number theoretic matter to check that for any integers, this is an existence result, for any integers r at least 1 and charge at least r plus 137, there exists a sequence A in this bold A, not necessarily unique, such that the symplectic bundle in the component YA from our infinite series have this prescribed rank 2R and second chain plus n. So that's all what I wanted to tell you. Thank you very much for your attention.
Thank you, Alexander. Are there any questions and comments? Okay, so
maybe I would like to add that one could ask me whether the similar, so to say, procedure could work on other threefolds, like Fano threefolds of main series, like quadric, intersection of two quadrics, section of Grassmannian, etc. I would say that for that you need to develop something like the theory of instantons, of symplectic instantons for them. But it is not at the moment well understood what we should mean by a symplectic instanton of higher rank on this Fano threefold. So this is an open field, so to say.
Thank you. So Fatma has a question.
Yeah, please.
Sorry, I didn't have a question. I don't know what happened. I'm sorry.
Yeah, so because you raised your hand, so I thought you wanted to ask something.
Yeah, sorry, I was not aware of that. Sorry, it was an accident.
It's okay. Any questions? So in your last theorem, in the end, you get these components of the moduli of rank 2 bundles.
Yes, right.
Of very high charge and very high dimension. Right?
Yes. Yes, and I show, we show that it happens for any numbers, prescribed numbers of charge and rank large enough.
Okay. Did you try to see what is the smallest charge that appears in these rank 2 examples?
That is what we already did with Sergei Tikhomirov and Danil Vasilyev. Actually, in this appears for charge less than 100. So
okay.
Less than 100, even around 30 or 40 at least.
Okay, thank you. Are there more questions?
Hi, Alexander.
Yes.
I want to ask you, in the choice of A's in the induction step,
yes.
they depend on the point or the component? I mean, is there something about boundedness that makes these A's to be chosen? I mean, the same for the whole component?
Yes, the same for the whole component. Yes, right. Not for a given point. We just do this for the whole component.
Okay.
That's it.
Okay. Yeah, so you select an open subset of the component for which a given A works.
Yes, right, precisely.
So you cannot have jumping. You cannot have on the same component two A's that...
I just shrink my component in order to avoid this jumping.
Okay.
That's it.
Okay. Thank you.
More questions or comments for Alexander. Okay, so let us thank him. Oh, Ugo has a question?
No.
So let's thank Alexander.
Thank you.
Did I raise my hand?
Marcos, you are moved.